right, so lesson 4, electric and magnetic interactions. So now we're kind of wrapping up the entire chapter. We've been talking about electricity, we've been talking about magnetism. Now we're going to really get into how do these things have to do with each other. So our guiding questions: how do magnetic fields affect moving charges? How can current be produced in a conductor? And how do generators and transformers work? Starting on page 266, we're going to look at the connect it. On the opposite page, page 267, we have a girl sitting there and she's got a fan blowing on her face. Circle the part of the image that shows that electrical energy has been transformed into mechanical energy. So think electricity into motion, because that's what mechanical energy is motion. So I want you to go ahead and circle that in the picture, and then you're going to explain how you think the fan works, and then list 2 other examples in which electrical energy transforms into mechanical energy. And then you're going to go ahead and pause the video if you need to, obviously. Anytime we do these answering things, pause the video if you need to. So magnetic force on moving charges. If magnets are placed around a wire with current flowing through it, 2 magnetic fields are actually at play. So think about that. We have an electric current going through a wire, put a magnet near it, right? So now not only do I have that magnetic field that it's being produced from the wire with the electric current going through it, I have another magnet coming into play for that. So we actually use what is called the right-hand rule number 2 to figure out the direction of the magnetic force on the moving charges. So as you can see in the image on the right-hand side here, using the right-hand rule number 2, kind of point your finger, just like you see in the picture there, point your index finger in the direction of the current and bend your middle finger so that it points in the direction of the magnetic field. Your thumb is then going to point in the direction of the magnetic force on the moving charges. So just another little kind of hand signal thing you can use to try to figure out the direction of the magnetic force. Motors use interactions between magnetic fields around loops of wire and magnetic fields between magnets to make things move. And we saw this yesterday when we were making the motors in class, right? You guys took that loop of wire, you had an electric current with the battery, we had a magnet. So we can create motors by these electric fields and magnetic fields interacting with each other. So when we have a loop of current in a magnetic field, so when a loop of wire with a current running through it is placed in a magnetic field, it will actually rotate, just like you see in the picture there. Where a straight wire moves in one direction in a magnetic field, a loop of wire will actually rotate. We use this tool called a galvanometer. It's a device that can measure small currents. It's actually the same tool that we use in fuel gauges. It's an interesting fact, used in lie detectors. So in your book, next to the image where we see the galvanometer, it says an electromagnet in the galvanometer turns the pointer to indicate the amount of current present. So it's kind of cool. You see in the picture on the left-hand side here, okay, how does this thing work? Why does an electromagnet act like a loop of wire in a magnetic field? So why does it act like a loop of wire? What did we say a loop of wire does, right? It's turning, right? Okay, so use that to answer the question there in your book. Electric motors. So what a motor is, it's a device that uses an electric current to turn an axle. It's going to transform electrical energy into mechanical energy. So we can see very simple process we got going on here. Loop of wire, we have a current running through it, and then we have a magnetic field. If you set that up, you can create motion. And it doesn't matter any type of motor that we're thinking of the motor in the fan, motor maybe in your toothbrush at home. All of these are the principles that make motors work.
In this video, we will look in simple terms how an electric motor works. You may wish to view these videos before we begin. You will have seen described before what happens when a wire carrying an electric current is placed in a perpendicular magnetic field. The direction of the field can be shown by Maxwell's corkscrew rule. If we add more wires, the resultant magnetic field builds up and becomes stronger. Placing these wires perpendicular to a magnetic field enables us to see how these force lines interact. Let's look at this setup from a different angle. Here we are looking down the wire. We can see a cross-section of wires and the magnetic field running clockwise around it. Now we can see the permanent magnets and the magnetic field between them running from north to south. These magnetic fields interact. Above the wire
these two fields run in opposite directions and so cancel each other out. Below the wire, the fields run in the same direction and reinforce each other. The wire is pushed away from the strong field towards the weak one.
So the wire will be pushed vertically upwards out of the magnetic field. This is the motor effect. Now, reverse the current. This experiences a force in the opposite direction. Now, place both wires in the same field. One wire will be pushed up, the other down, but we don't have circular motion yet. Now, if we link the wires together and then insert a spindle to allow a rotation, we convert the opposing up-down motion into a rotation, and here you have an electric motor. Looping the wire around many times will increase the turning force on the motor. The clever bit is how to supply a current to a spinning coil so that it always flows in the same direction, ensuring that the upward and downward forces are always on the same side. This is done with a split ring commutator, but the exact details as to how this works we can leave for another time.
If you like the video, give it up.
All right, so on page 269, we have a diagram, figure 5, and it's showing us how a motor works. So you can see here we have very basic parts to how a motor works. So even though you guys made one yesterday, here they are. We just have sort of like the fancy words for it. So a motor is made of several basic parts, each of which is described below. Study the information about each part, then write the number of each description in the appropriate circle on the image. So number 1, where are the magnets at? So producing a magnetic field, and as we saw, this is what's going to cause the armature to turn. The second thing, the commutator. It consists of 2 semicircular pieces of metal. It conducts current from the brushes to the armature. So semicircular is the key word there. Brushes, which do not move, conduct current to the rest of the commutator. Number 4, the armature is a loop of wire that the current flows through. So where's that loop of wire? And then finally our power source, number 5, the battery. So go ahead and label those. What is the only part of a motor through which a current does not flow? So let's think about, when we look at all of these parts here, where's the only part that a current is not flowing? So on page 269, you want to make sure and go through and number all of those parts, and then you want to go ahead and read or correct the answer or write the answer down there in the reading check. So electromagnetic induction, it's the process of generating electric current from the motion of a conductor through a magnetic field. So when we think about this, this is the opposite of what we were just talking about. So we created mechanical energy turning by the production of taking that electric current, interacting with a magnetic field, but an electromagnetic induction. So now I have generating electric current from the motion of a conductor through a magnetic field. So it's the opposite. Mechanical energy is transformed into electrical energy, producing an induced current.
Hello. Oh.
All right, so in your book on page 270, we have another picture here. Figure 6. When a conductor, as we saw in the video, such as a metal wire, moves through a magnetic field, current will be induced in the conductor. So think of a conductor, something made out of metal, right? If I move that in a magnetic field, current will be induced. So you're creating electricity. Examine the image, then use the term clockwise or counterclockwise to complete each sentence correctly. So if I look in the figure on the top here, a wire conductor moving up through a magnetic field induces a current in one direction. A wire conductor moving down through the same magnetic field induces a current in the opposite direction. So we're going in opposite direction. So you're going to go ahead and answer when the conductor moves upward through the magnetic field, the induced current flows, and you would answer either clockwise or counterclockwise by looking at the picture, and then the same thing for the second one. On 271, induction from a moving magnet. Current will be induced in a conductor in a magnetic field when the magnetic field moves in relation to the conductor. So a magnetic field moving up through a wire conductor induces a current in one direction. So if I look at this picture on the left here, I see the magnet moving up, magnetic field in one direction. When I move the magnet down, a magnetic field moving down through a wire conductor induces a current in the opposite direction. So on 271, we have a reading check question. Based on figure 6 in the previous slide and figure 7, what are the two ways that a magnetic field can change relative to a conductor? So what can we do to that magnetic field relative to the conductor? So alternating and direct currents. Direct currents, or also known as DC current, is current that flows in one direction only. It is current that comes from a battery. When batteries produce power, they produce power in DC current. Alternating current, AC current, is current that alternates direction, goes back and forth and back and forth. Much more common than DC current. A benefit to AC current is voltage can be easily changed. This is how electricity is delivered to our house. So running through the power lines outside, it is AC current that is getting delivered to us. It is more efficient to get power to people using alternating current than direct current. So on page 272, what is the main difference between AC and DC? So really all you got to do is look at the definition there and go ahead and answer that. Alternating current was developed by Nikola Tesla. So super cool guy, crazy smart. When he came up with this, it was really innovative and really helped out communities trying to get power to people. On 272, our question. Types of current, figure 8. It is not uncommon for one object to require both direct and alternating currents to operate. An electric car is one item that requires both AC and DC current. Write a question about the use of AC and DC in the car. So what are questions when you think about that? Maybe, what is AC current used for? What is DC current used for? That would be a very easy question you can answer there. So generators and transformers. So all a generator is something that transforms mechanical energy into an electrical current. It makes electricity for us. And if you'll notice, it's literally the reverse of a motor. So motors take electricity and they turn things. Generators get things turning and make electricity. So anytime you guys see a generator, it doesn't matter if it's running off of gasoline, it doesn't matter if it's running off of natural gas, it's taking that and turning it into electricity. So on 273, so here we have, this should look similar to us, right? Looks similar, but it's not. It's the opposite. It's a generator. So figure 9 is a generator. A generator works when its component parts operate in the correct order. Number the part names in the correct order to show the operation of a generator from the magnets to the moment when the current is produced. So you're going to write it in order. This isn't labeling like the last picture, what's first, what's second, what's third. So you're going to have it in that order. Then circle the names of the parts of the generator that you would also find an electric motor. So make sure you go ahead and circle in there what's found in the electric motor.
Hall of Fame in Dawsonville to see how we harness electricity and magnetism to get where we want to go. We're looking at generators and motors in this segment of Physics in Motion. You may not have known, but generators and motors are not the same thing. We're going to use this vintage car to help explain the difference. Let's look under the hood. We're first of all interested in the generator, which is right here. It takes mechanical energy from the engine and turns it into electricity to run the lights and wipers and all the electrical systems in the car. A motor works the opposite way. It takes electrical energy and turns it into mechanical energy. So motors and generators are the reverse of each other. We'll get into more detail on all this a little later, but first, let me explain the difference between a motor and an engine, because many of us use those terms interchangeably. Technically, an engine runs on fuel, like gasoline. Motors, on the other hand, use electromagnetic induction. So if it needs chemical fuel, it's an engine. If it doesn't, and it runs on electricity, it's a motor, whether it's your electric toothbrush or a Model S Tesla. So now let's talk about how most cars, electric cars accepted, use generators and motors. It might be a little different than you think. Before about 1960, most cars used generators to drive the electrical system and gas to run the engine. Most modern cars use an alternator, which is a slightly different kind of generator for the electrical systems. But motors and generators both use electromagnetic induction, in which voltage is induced by a changing magnetic field. Okay, so you know that electricity can generate a magnetic field, and vice versa. But what you may not know is that this discovery, hundreds of years ago, led to figuring out how to build a car, and it starts with a man named Michael Faraday. He's the guy who invented the generator, which changed just about everything having to do with machines and how they work. Today, he's considered one of the greatest scientists who ever lived. One of his many legacies is called Faraday's Law. It predicts how a magnetic field will interact with an electric circuit to produce an electromotive force, or EMF. This interaction results in the phenomenon we call electromagnetic induction, which creates a current in a circuit when there is relative motion between the wire and the magnetic field. I'll show you in a simple demo. When I put this magnet through this wire loop, the changing magnetic field creates a current in the wire. You can see it here on the voltmeter. It induces a voltage, and that difference in potential causes current to flow. You can also see how electric current induces magnetism with this wire, nail, and battery. Normally, this nail is not a magnet. But when it's wrapped in a coil of wire, and I cause the current to flow by attaching it to a 6-volt battery, it becomes a temporary magnet. Now let's get into more of the guts of motors and generators. We'll start with motors. The most basic type of motor is a DC, or direct current motor. Direct current is electrical current that runs in only one direction. Current travels from a battery and moves through wires called brushes, because in the old days they actually were brushes. Today, there are also brushless motors, which use digital sensors to perform the same tasks. The brushes sit on a piece of metal called a commutator. The commutator is a split ring, usually made of copper, that is connected to wire loops known as the armature. The commutator armature assembly is known as the rotor, which rotates at the center of the motor. The brushes, or sensors, are connected to the battery and make contact with the commutator as it turns, supplying it and the armature with current. This assembly sits in a stationary magnetic field that is created by the stator, made of either a permanent magnet or coil-wrapped metal plates that surround the rotor. The field exerts a magnetic force on the wires, which causes the rotor to turn. When the rotor has made half a turn, the current begins to flow in the opposite direction, because the commutator is now touching the opposite side of the battery. This electromechanical process, by which direct current is turned into alternating current, is known as commutation. That reversal of current causes the magnetic force acting on the rotor to reverse direction. When it reverses, it makes the rotor spin. That motion, that mechanical energy, can turn a shaft, which is connected to many things to make them run. Your house probably has at least 50 motors in it, running everything from power tools and fans to household appliances and electric cars. There's another type of motor, an induction motor, that runs directly off alternating current. Compared to DC motors, induction motors are simpler and have fewer parts, no brushes and no commutator, which makes them more reliable and longer lasting. While induction motors run on alternating current, DC motors run off direct current and are used whenever the motor is battery operated. This is the stator, which in this kind of motor is made of laminated magnetic metal plates. It doesn't move, it's stationary, just like in the DC motor. Copper or other metal is wound through to form a coil. Sometimes we call them windings. The more loops the windings have, the greater the magnetic field is through them. When you hook up the alternating current to the stator, the changing nature of the current flow creates a rotating magnetic field around it. The stator doesn't move, just the field around it. Like DC motors, induction motors have a rotor at the center made of copper wires. Remember, Faraday's law tells us that the changing magnetic field created by the stator induces voltage in the rotor. And because of that induced voltage, the rotor, located at the center of the motor, becomes a current-carrying loop. The changing magnetic field around the stator exerts a magnetic force on the current-carrying rotor, which causes it to rotate. As the magnetic field moves around the rotor, it exerts a force in just the right place to cause the rotor to continue to rotate. That's what causes the rotor to spin continually, exerting a force on the wires at just the right time to create optimal power. We've seen that electricity and magnetism are intrinsically related. Alternating current flowing through the wire in the stator creates a changing magnetic field, and conversely, current flows in the wires of the rotor because of this magnetic field. All motors function in much the same way, in that they all need changing magnetic fields to create motion within the rotor. The fundamental difference between induction and DC motors is that the changing magnetic fields in an induction motor are caused by the alternating current that is supplied to the stator. In a DC motor, the changing magnetic field is caused by commutation, which, as you recall, is the mechanical transformation of the direct current from the battery to alternating current through the brushes and commutator bars on the armature that make up the rotor. Let's step back a second and think how we could make this motor even more powerful. Let's use the equation that allows us to find the magnetic force exerted on a current-carrying wire, where magnetic force equals current.
All right, I think Mrs. Eskla is going to stop it here. She's starting to get into.
Magnetic field strength.
Let me skip through.
That we've talked about. Each loop contains moving charge that experiences a magnetic force. The more loops, the stronger the net force of the rotor, and so the more powerful the motor. Now that we've seen how motors work, let's take a look at how generators work opposite the way motors do. They take mechanical energy and turn it into electrical energy. This is a generator. It's found in classic cars built before 1964. Just like certain types of motors, it has a rotor made of an armature and a commutator that are in contact with brushes and an electromagnetic stator that surrounds the rotor. The difference is the armature rotates through mechanical action provided by the engine, being linked to it through a pulley. There's a residual magnetic field within the stator that provides the initial push to start current flowing through the armature as it rotates. Some of the current produced by the moving armature flows to the stator, strengthening the magnetic field and increasing output. In this car, the excess current from the armature is used to power things like headlights and turn signals, as well as charge the car's battery. There are many different kinds of generators, but they all follow the same principle, taking mechanical energy and turning it into electrical energy. So question, between motors and generators, which one do you think supplies electricity to your home? That would be a generator. So a power plant consists of an electrical generator. something has to spin the rotor within that generator. It might be a water wheel in a hydroelectric dam, a large diesel engine, or a gas turbine. But in most cases, the thing spinning the rotor is a steam turbine. The steam might be created by burning coal, oil, or natural gas, which heat the water to create the steam. Or the steam may also come from the heat generated by a nuclear reactor. And the electricity that results is in the form of an alternating current. Alternating current, or AC, is current that reverses direction multiple times per second. In the United States, that happens 60 times per second, or 60 hertz. AC power uses high voltage to move the electricity long distances. During transport, the voltage is so high that it's too dangerous to use in residential or even commercial use. A power plant creates electricity that can be stepped up or increased to as much as 500,000 volts. But by the time it gets to your house or business, it's either 240 or 120 volts. How do they do that? Companies use transformers to lower the voltage to a manageable level. By the time it gets to you, the voltage has been stepped down by transformers several times, so that you can safely run all the electrical devices around you. We've talked about the difference between generators and motors, how they mirror each other in some ways, but both supply us with the energy we need to power our world. And we saw some really great cars while we were here. That's it for this segment of Physics in Motion. We'll see you guys next time.
All right, she got into some upper level things there, but definitely covered all of the stuff that we need to. So transformers, you may not have known this is what you were looking at before, but here's a transformer. So what a transformer does is it either increases or decreases voltage using two separate coils of insulated wire wrapped around an iron core. So when that power comes from the power company, we need to get it so it's stepped down into our house. So you guys will see a transformer like you see on the pole there. But out of the power company, if they need to step up that power to really get it pushed out to residential homes, you guys will see transformers, step up transformers. So step-up transformers increase voltage, the electricity leaving power plants. Step-down transformers, like we just said, decreases the voltage, electricity going into homes and businesses. So what you see in a transformer, inside of it, is you have these coils, and one of them is called the primary coil, and one of them is called the secondary coil. In a step-up transformer, the primary coil has fewer loops than the secondary coil. In step-down transformers, the primary coil has more loops. So here's a step-up. So the primary coil has fewer loops, and a step down, the primary coil has more loops. There's a formula that we can use to actually figure out what the voltage is. It's this nice little ratio formula here. So on page 274, you can figure out what the voltage difference is going to be by using this formula. So you can take primary voltage divided by secondary voltage equals primary loops divided by secondary loops, and use your cross multiplying to answer those questions. So on 274, you need to go ahead and answer questions 1 and 2. And then finally, on page 275, we have 4 really simple wrap-up questions that you're going to answer to wrap up lesson 4.